All right, today's a fun lecture. It's going to tie in a lot of the stuff we've done recently. So, what have we done recently? So, the past few weeks hasn't been just about solving problems. It's about kind of understanding problems. Some problems that are easy, some problems that are hard. Starting with something like Boolean sat, trying to decide if you can satisfy a Boolean formula or not. And we also looked at special cases and like 3-sat, and I'm not sure what seems to be some issues. Okay, not sure what's going on with the software, but hopefully it's okay. Okay. And we did other problems, things like 2-sat, max 2-sat. We talked about the differences, in particular. Max 2-sat turned out to be just as tough as 3-sat, whereas regular 2-sat wasn't. Right, okay. So subset sum, that was tough. Longest path, hard on regular graphs, easy in DAGs. In last class, we talked about independent set, which is trying to find a set of vertices that don't neighbor each other, as well as special cases of graphs, like interval graphs and trees. We had our usual vote and stuff like that. What did we show? We showed that independent set in general is hard. It can be used to solve 3-sat, but for both interval graphs and trees, we came up with some dynamic programming based algorithms. Okay, so today's lecture is going to try to bring all these problems together and wrap it all up. So, okay, so it's going to be a little bit more conceptual than usual. I'm trying to prove a theorem called NP completeness. Okay, so the first step of our argument, I'm only going to make a somewhat of a high level because a more detailed discussion would require a certain amount of background that typically appears in like a complexity theory class. Let me first state kind of the claim at a high level. I'm going to try to argue that we can think of any computer program that's running on a CPU as a circuit. Okay? And in particular, a polynomial time program will correspond to a polynomial size circuit. Okay? If I had more time or took more time, I might discuss very formally I might really formally try to define what is a computer and stuff like that. And we have discussions about things like Turing machines, which is an abstract model proposed by Alan Turing, but generally encompasses all computers. But that'll take quite a while. So I'm going to try to give a little bit more of a conceptual, slightly hand-wavy proof, but roughly to the same effect. And hopefully the ideas will at least make sense. But it won't be quite as formal as some of the other things we do. All right, so let me try to argue that I can try to think of any computer program as a circuit. This is going to be our first step towards a grander conclusion by the end of class. All right, so we're going to look at sort of a simplified model of computing where I just have a CPU, meticulously drawn there, and memory, RAM. Okay, and I want to think of CPU as just some kind of like logical circuit. It takes in some stuff, it outputs some stuff, right? So I think of a CPU as maybe a lot, but ultimately a constant number of circuits. The number of circuits that the CPU is composed of is independent of the size of the memory. Okay, the memory is generally otherwise unbounded. And in our simple model of a computer, the CPU reads from RAM, writes to RAM. Okay. So a little bit more formally, well, I don't know if it's that formal, but let's say that in every step, the CPU will say read from 2 locations in memory, some x and some y, and maybe add them up and get x plus y and write that out to another place in memory, right? So, maybe this is saying x48 is 410 or 78. So roughly, if I went to row 4, and I can't count to 10, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this might be x410. It goes into the CPU, and we have 7 and 18. 1, 2, 3. Okay, so maybe in one step you'll read in 2 bits of data, and it gets written out to, I guess, uh, something like that. Okay. So I'm thinking of a kind of a very simplified model of computing for the sake of discussion, and just pretend that roughly all computer programs can kind of boil down to doing this kind of step, one step at a time. Okay, read in a constant number of bits, write out one bit to some location in memory, and repeat, 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 repeat until it ultimately decides yes or no on whatever question. So simplified model of computing. All right, so okay, now the high level goal is to argue that any program in this kind of simplified computer can be understood as a circuit, but it's not really totally a circuit. What's sort of the main conceptual difference, I'm asking you guys, between like a real normal circuit on the left and what this computer is doing on the right, simplified computer? There's one kind of distinct difference. Yeah, well, let's say that maybe you can have, what you can do is you can like allocate one spot for the output or something. And so at the end of the day, once the computer finally writes a 1 or 0 there, then it's done, and that's the output, 1 or 0. Yeah, okay. So let's say they still both output 1 bit. The circuit clearly outputs 1 bit. But maybe, yeah. Yeah, it can have loops. It can have loops. And maybe another point is at some level, so the circuit, nice thing about the circuit is like, the node in the middle, it evaluates its two children or whatever, and it gets an answer. And that's the answer right there for that gate forever. And for the CPU can actually write to the same location over and over again in RAM. Otherwise, they're both kind of doing the same thing where they're gradually evaluating logic, right? They start with some input bits and they gradually evaluate logic until they output 1 bit. But one thing a little bit different is that the circuits sort of have like a completely different node allocated, for every intermediate computation. But, loops is definitely a place where this occurs, but a CPU can reuse memory and write to the same location, or read to the location, right, and stuff like that. Okay, so at least for the sake of this discussion, I'm going to say that's really the main difference between the two models, is that you sort of have these like, when you rewrite to memory, that also means you sort of have like cyclic dependencies on those, like where you're writing the data. Our circuits are always acyclic graphs, right? They always just like go up. But here, you write in some, you have some variable I, you write to it, you update it, and then you can come back to I can later in time depend on the previous value of I and stuff like that, right? So, okay, so you get these kind of weird cyclic dependencies in the logic, so to speak. Okay, so the conceptual question is, I still want to try to think of computers as circuits, and the main conceptual obstacle is that I can rewrite to the same place in memory. That I see as the big difference between circuits and computers. So how can I try to conceptually, remove sort of these cyclic dependencies in memory, right, to make it look more like a circuit? Yeah. Strongly connected components, would that be a solution? It's a good connection, but I think no. Maybe we can reinterpret what we eventually do, but I don't think so. How can I, yeah. Some level, how can I think of the computers in, yeah. Okay, so yeah, if we can change the program so that I never write to the same place in memory, right? Suppose every step wrote to a different location. then it'll be kind of easy to think of, okay, now how do I take that program that's always writing to a different location? I can turn that into a circuit where each location becomes an intermediate node, right? And then every time the CPU does something, that's some, gate, right? Okay, so if I can change the program so it never writes to the same location, then I basically have a circuit. Now, how can I kind of argue, or what's a lazy, and by lazy I mean very general, way to guarantee this, and guarantee this is possible? Surely, maybe for a small program, we could go through and change it by hand, but I want to argue that any program can be changed to avoid rewriting to the same location.
Every time you create a new variable,
Yeah, so what's a convenient, slick way? It might not be super efficient to guarantee we can come up with new variable names, we can remember everything, and because I want to try to make an argument that I can always do this in general, which is an awkward argument, right? It's a bold claim. Yeah. Induction? Maybe, but I think it'll get a little hairy though. Probably it requires more detail than I'm presenting at it. As any other tricks, I guess. Yeah, maybe we can try to get an n-step program and get it down to n-1 or something. I don't know. Let's see. Sometimes when I'm writing an essay or something, when was the last time I wrote an essay? I don't know. But I'm going to go in and I'm going to change something, right? But I kind of want to keep the old version and not screw it up, right? What would you do? Make a backup, right? You copy and paste the document, and then make a change in the new version so you have the old one, right? Something lazy we can do that kind of works very generically is each step, just copy the whole data over to like a new. We're going to roughly index the state of memory by time, right? So time t equals 0, there's some set of data, right? It's 1 gigabyte of data. Now I just imagine having another set of 1 gigabyte at t equals 1, where I copy everything over, except when I make that one change to one location from time 0 to time 1, I'll change that 1 bit, right? And then I'll make another copy to go to time t equals 2, and then I'll change 1 bit. Another copy to times t equals 3, change 1 bit. The nice thing about this, obviously it's sort of wasteful, right? Because everything's just ballooning. We'll talk a little bit about just how big it's getting in a moment. But it's very generic, right? In the sense that I don't have to assume anything more than kind of what I know about this model. Like it's quite possible that some induction argument might be possible, but it requires probably more details about what we're analyzing. This argument can be made at the level of just this relatively abstract model, where all I know is that I read in a few bits and I output one new bit. Okay, so we can imagine, taking this computer and to turn it into a circuit that never, or roughly to make sure it never writes to the same location of memory. If the program is going to use 1 gigabyte and run for 100 steps, it's now going to use 100 gigabytes. Okay, so where in each step I copy everything over except I update 1 bit, update 1 bit. Okay, so a simple trick. I'm not saying this is practical. I'm just trying to make a theoretical argument. Theoretically, a sound argument. Okay, so to sort of remove these cycles of memory, we parameterize by time. We roughly make copies for every time step. Okay. All right, so that takes a program on our simple model of computing and turns it into a circuit because we're never rewriting to the same location of memory because every time step I just make a new copy of RAM. All right, so I think the main objection you guys might have in mind is, isn't this a huge race? I mean, isn't this a terrible idea to copy everything over, even though it's nice and clean? So let's see how big this circuit really is, right? How big, imagine, there's n steps in the algorithm or something, right? So this thing goes on and on and on. But ultimately, how big is the circuit? Order n. So what's n? Okay, the number of, okay, so there's one copy for every time step, right? Okay, so that's something. Okay, and so number of time step times what? Yeah, times the size of the memory. Okay, so uh, one sec. Okay, first we do have like the CPU at every step, so that gets repeated. There's some circuits in there. Plus, so I got too clever with my hiding. I can't figure out how to erase. Okay. Oh, what have I done? I ruined my lightning bolts. All right. So in general, the size of the circuit will be the size of the CPU plus the size of RAM for every time step, right? So that's just an upper bound on the total size of this circuit we've created out of a computer program. Okay, and then how big is the RAM, or what's a reasonable upper bound on the RAM? Or how much RAM do you need, yeah? Input and output, so input is some input size, output is just 1 bit. But you might need more, right? I mean, you read in some data, and you write some data, but you do other stuff. The question makes sense. Okay, so memory needs to be big enough for the input, needs to be big enough for the output, that's fine. But I also need, there's some intermediate calculations, right? How do I upper bound the size of the space used for that? Size of what? Search? Oh, well, the circuit might be, I mean, the CPU, some constant size, the RAM can be very big, right? It's sort of a weird question, but does the question make sense? How big does the RAM need to be? It needs to contain the input, that's true. It does need to contain the output, that's also true. But it also needs to account for all the intermediate writing and reading. So how can I try to bound how much reading and writing I do in the middle, or writing in particular? Yeah. Depends on the program, yeah. So it's got to be something very general, right? Because you don't know any details about the program. Sorry? Number of what? Nodes? What nodes are there? Sorry? In the circuit. Number of nodes in the... So I'm asking, how big does the green grid need to be? One of those green grids. It should be just some, right? Yeah. Okay. So you need memory to contain your input, your output, and beyond that, you can only write one piece of data every time step, right? So a reasonable upper bound on the size of RAM will be, say, I excluded output because that's only 1 bit. Input size plus the number of time steps. Right? I need to write down the input, and I'm only going to write one thing per time step.
But we only have the copy for each time step. But why do we still need number of time steps?
Well, okay, let me go to the next part. So, all right, so if I multiply all that together, right? So if I'm looking at a polynomial time algorithm, I really want to argue that a polynomial time algorithm is going to map to a polynomial size circuit. So now the number of time step is some polynomial. Okay, so overall my total size of my circuit is what? You know, a constant times the size of RAM times some polynomial in input size. And the size of RAM is the input size plus a polynomial in the input size. Okay, so I plug everything in, multiply it all together, and we get that the total size of the circuit is bounded above by a polynomial in the input size. If the program is a polynomial time algorithm, like it always terminates in a polynomial number of steps. Maybe it's n cubed, maybe it's n to the fourth, it doesn't matter. So that's why I was interested in bounding the size, because in particular I want to argue that a polynomial time algorithm, however clumsy and heavy-handed this trick is, still maps to a polynomial size circuit. It's an n squared algorithm, I guess it's looking like an n to the fourth size circuit or something. Okay. All right, so any questions? A bit hand wavy, but it's faster this way. Okay. All right, so that was step one of the grand argument, to argue, at least at a high level, that I can think of any polynomial time program as a polynomial size circuit. The polynomial blows up, but it remains a polynomial. Okay. The next step for us is to argue that every search problem can be interpreted as a circuit SAT problem. Another big, grand statement. Okay. I want to argue that every search problem is a circuit SAT problem. So what's a search problem? All right, so all of these problems we've been doing the past few weeks, right? Some of them were obviously decision problems, SAT and subset sum, right? Is there a satisfying solution? Is there a subset that adds up to T? I could think of independent set of decision problem where I say, oh, is there an independent set of size at least K? That's a yes/no question. Hamiltonian path, is there a Hamiltonian path, right? All these yes/no questions that we're having a lot of trouble with. The one thing they have in common is that if the answer is yes, they have a very simple certificate or proof, right? If I asked you, is there a Hamiltonian path in this graph? And you said yes. And I said, prove it. What would you do? You just give me a path. Say, hey, look at these nodes in a row. That gives you a Hamiltonian path. And it's very easy for me to double check. Oh yeah, okay, you're visiting all the nodes and these are all following edges and you're not visiting any nodes twice. It's very easy for me to verify a yes answer with some form of a proof or certificate. That's also true for subset sum. Give me the numbers, right? Satisfying formula. Give me the satisfying assignment. And I can check it's correct very easily. So while we don't have algorithms to actually construct an answer, it's very easy to write an algorithm to verify an answer. So in that general sense, we can think of it as a search problem. You know, because when you're looking for something, but you can at least recognize what you're looking for. Okay. All right, and that's okay. So we want to argue that any problem of this format, where you're looking for something that you can recognize when you do find it, can be solved by circuit SAT. All right, so here's how I usually try to make this argument. So have you guys seen this movie? This might be before you're born or something. Okay, so this is Good Will Hunting. So Matt Damon plays Will Hunting, who's like some kind of mathematical genius from Southie, Boston. And Ben Affleck, his character's name is Chucky, is his friend who is not a mathematical genius, but otherwise from the same neighborhood, Okay, otherwise kind of more a normal guy, and they're best friends. Okay, and they get drunk every weekend. Okay. All right, so Matt Damon is sort of a all-powerful computer, and Ben Affleck is bounded to polynomial time computation, stuff like that. Okay. All right, so let's say that we're looking at a SAT problem. Okay, so you're given some formula and you want to know, right? Some 3-SAT problem. All right, so Chucky and Good Will Hunting are talking, and that should be F, not phi. But Chucky or Ben Affleck asks Will Hunting, is this formula satisfiable? Is this formula satisfiable? And Will Hunting's a very smart guy, even though he's a janitor, and he thinks about it for a little while, and then he just says yes. There's a satisfying solution. Because he can do that. He's Will Hunting. He can solve SAT. Okay. So then Ben Affleck says, okay, I don't believe you, right? I don't believe you. You're full of crap. You make stuff up all the time. I don't believe you, right? So Will Hunting says, okay, well, here's a satisfying solution. Set x1 to be false, set x2 to be true, and so forth, right? And so poor Ben Affleck, who wasn't able to find a satisfying assignment, he can still at least verify Will Hunting's solutions. That's within his range. So he spends some polynomial amount of time thinking and double checking that the Will Hunting solution is correct. Okay, and then he says, okay, cool, I believe you, right? Now what does Will Hunting say? No. Will Hunting says, how you like them apples? Okay, because that's what Will Hunting does. All right. Okay, but the point is that even though Ben Affleck can't solve SAT, he can verify a SAT solution. That he can do. Anyone can do that. Okay, another example, independent set. You give an instance of independent set, right? So you ask Google or Ben Affleck asks Matt Damon, is there an independent set of size k in this graph? Will Hunting is a genius, thinks about it, says yes. Ben Affleck again says, I don't believe you. Will Hunting says, okay, well, look at these vertices, V1, V2, V3. That's an independent set of size k. Ben Affleck says, okay, let me get back to you. I'll double check. Spends a polynomial amount of time double checking that it is, say, an independent set. Will Hunting or Ben Affleck says, okay, cool. I believe you. I double checked. It's correct. And Will Hunting says again, how you like them apples? And Ben Affleck says, please stop. Okay. All right. But you get the exchange, right? So even if you can solve it, the point is that you can verify it even without, infinite computing, right? It's easy to verify these answers. Okay. So all these problems that we've been so preoccupied with, and they look simple and we couldn't solve them, but we do know that they have certificates that can be verified in polynomial time. That's roughly all they have in common. So that's all I'm assuming about these problems, that they have some polynomial time verifier. Okay. So, yeah.
If we are not given the answer, even if we get if we know if there is or not, it's not enough information to verify to be true. We need
So you need the certificate. Yeah, if Will Hunting just says there's a Hamiltonian path, but I wouldn't believe him until he actually provided the Hamiltonian path. Right, so that's the importance of this word certificate. There's some compact, right? Those are also small proofs. They're not like exponentially large, right? Hamiltonian path is, of polynomial size because it's just listing off n vertices.
I'm not sure if it's really the difficulty checking existence or finding a specific path.
Yeah, so actually, a search for us, a quote unquote search problem, is defined simply as any problem that has this kind of efficient proving format, where you can provide a certificate that can verify yes in polynomial time. That's the definition of a search problem. So those are just examples of search problems. In fact, they don't even have to be hard. I mean, there could be easy problems like shortest path or something also count. But okay, because I really want to argue that CircuitSat will solve any search problem. And those are 4 examples of search problems. Okay. And all I'm assuming is that we have a polynomial time verifier for some kind of certificate. Okay. So, the key point, right, is when Chucky or Ben Affleck is thinking, right, for a polynomial amount of time, okay, there's some kind of computation. There's some kind of algorithm, right? There's something that runs on a CPU and RAM, and right, there's a computer program that runs in polynomial time and can verify an answer, right? Answers yes or no. This is a Hamiltonian path. This isn't a Hamiltonian path. This is a satisfying assignment. This isn't a satisfying assignment. That we can do in polynomial time. And what do we now know about all polynomial time algorithms? Or what did I sketch at a high level? All right, so what do we know about polynomial time algorithms? They can be converted to a polynomial sized circuit. So I know that if there's a polynomial time algorithm that has to verify something is a Hamiltonian path, then I also know there's a polynomial sized circuit to verify that something is a polynomial, something is a Hamiltonian path. All right, so that's all I know. So a polynomial time, okay, so that means there's some polynomial sized circuit, right? Instead of thinking of Ben Affleck as an algorithm, I could think of him as a polynomial sized circuit. Okay, so what does that all mean? For some reason I put that here twice. Okay. Okay, so all the problems we've considered have certificates that can be verified in polynomial time, which is also, but a polynomial time verifier implies a polynomial sized circuit. So all of these search problems, for any search problem, there exists a polynomial sized circuit to verify a certificate. Okay, the existence of an algorithm gives us the existence of a circuit. It's not really too important exactly the construction. All that matters is the existence and sort of that conceptual connection. Okay, so in that way, we can take any search problem and produce a circuit. Okay, so that a circuit SAT solver will tell me if, okay, so let's take, for example, independent set, right? Suppose I have a black box that can solve circuit SAT, and I want to solve independent set, right? At least in theory, there exists a circuit to verify a solution for independent set. So that circuit takes as input a list of vertices and outputs true if it's an independent set of size at least k, outputs false if it's not, right? All it's doing is verifying a solution. So there exists a circuit, we can construct it, and we can feed that circuit to a black box, right? That circuit only says yes if there is an independent set of size k, or you can only says yes if you give it an independent set of size k. Circuit SAT asks if this circuit has a satisfying assignment, right? So if the circuit verifies independent set, then what that black box is really going to do is tell you if there is an independent set of size k in the original graph. Same with Hamiltonian path. You give an instance of Hamiltonian path, I can make a circuit, right? And this circuit will take as input, a list of vertices describing a path, and the circuit will double check that it is a Hamiltonian path in the graph, and it'll answer yes if it is, and no if it isn't. right? There's a circuit that verifies Hamiltonian paths. It's not a circuit that finds a Hamiltonian path. There's a circuit that verifies a Hamiltonian path in the graph, right? If I feed that to the circuit sat black box, the black box says yes, it's saying, okay, there's something that makes that circuit happy and output true. But for the verifying circuit, that means there is a Hamiltonian path in the graph. If the black box says yes, or if the black box says no, then it's saying there's no input that leads to that circuit outputting true, which means there is no Hamiltonian path in the original graph. But the key point of this argument is that not really requiring much structure that closely related to the Hamiltonian path problem or the independent set problem or the subset sum problem or satisfiability. Only the fact that it's a search problem and there exists a polynomial time verifying algorithm. And so at least in theory, that can be converted into a circuit. Okay, and such a circuit could be fed into a circuit sat black box. Okay, so it's saying that circuit sat can solve any algorithm, any problem that's a search problem. No, I did a little bit of hand wavy in terms of going from a polynomial time algorithm to a circuit. Okay, but that's not too important, the exact details. It's the connection that's important. Does this make sense? All right, so not sure why I have the same slide again. Oh, okay. Yeah, all right. Okay. So the conclusion is that circuit sat is the hardest possible search problem in the sense that circuit sat will solve any search problem. All right. So now let's put together everything that we've learned for the past few weeks, right? So we looked at a bunch of problems that are search problems, like independent set and subset sum, right? Now we know that circuit sat solves them. Okay. But what else do we know about the relationship between circuit sat and, for example, Hamiltonian path? So earlier we showed that if you can solve Hamiltonian path, then you can solve 3-SAT. Before that we showed if you can solve 3-SAT, you can solve SAT. And if you can solve SAT, you can solve circuit SAT. Right? And now we just looped it back together. If you can solve SAT, you can solve Hamiltonian path by the Cook-Levin theorem. Okay? So all these problems are polynomial time equivalent. If you solve one, you solve all. Okay? So altogether, okay, it all kind of comes together, right? So, okay, so maybe two things to define. Okay, so NP stands for non-deterministic polynomial time, which is a ridiculous name. In my mind, it always means not polynomial, but it's not actually what it means. Okay, so non-deterministic polynomial time. That means if you had a computer that, like, in each step can split the universe into two parts and try two different things, and keep splitting and keep splitting and keep splitting, and take a polynomial number of steps, and it would terminate in a polynomial number of steps. But this is roughly any problem that can be solved in brute force. Like, so the first step, you guess the first bit of the answer, or of the certificate. The next bit, you guess the second. Next step, you guess the second bit, third bit, right? So if there's a polynomial number of bits in the certificate, then you can just guess a certificate in brute force. Okay. But anyway, I think, so that's why the name is the name. But NP is really any search problem. Okay, so anything that has a polynomial size verifier or polynomial time verifier is really the definition of NP. Okay? Any such algorithm can be solved in non-deterministic polynomial time, but that's sort of silly. Okay, so NP refers to any problem with a polynomial time verifier. NP hard, a problem is NP hard is if it can solve any other problem in NP. Okay, so circuit SAT is NP hard, because we know that any problem in NP, which is to say any search problem, can be solved by circuit SAT. Okay, so that's an example of an NP-hard problem. A problem that is in NP and in NP-hard is called NP-complete. Okay, so that means it's a search problem. If the answer is yes, there's a way to verify it efficiently. And it's NP-hard, meaning it can solve any other search problem. So CircuitStat is the first example. We can use CircuitStat to solve any search problem by this kind of abstract argument, Cook-Levin theorem. And on the other hand, we know that CircuitStat itself is a search problem because a satisfying assignment is easy to verify. Okay. If I take like Hamiltonian path is an NP because it's a search problem. I can verify a yes efficiently. And it's NP hard because we showed a few classes ago the Hamiltonian path can be used to solve CircuitStat, and CircuitStat can solve anything else in NP. So Hamiltonian path is also quote unquote NP complete. Okay, so all four of those examples, SAT, independent set, Hamiltonian path, subset sum, are all examples of NP complete problems. They're in NP because they're search problems, and they're NP hard because they can solve SAT. Okay. So all these NP complete problems, we don't have an algorithm for, but if we have an algorithm for any one of them, a polynomial time algorithm that is, for any one of them, we'll get a polynomial time algorithm for all of them. And that's where we stand. Okay, we've been stuck here for like 40 years. Okay, so this theory of NP completeness refers to this giant deadlock. Okay, and the question of whether we can get a polynomial time algorithm or prove that it's impossible to get a polynomial time algorithm is like one of the most outstanding problems in science, problems in math, problems in computation, right? But it stretches into a lot of things, right? I mean, this definition of, because at a high level, you don't have to think too much about like a literal computer. The more abstract statement of, things that have proofs, can they all be solved? Right? Things that have efficient proofs, can they all be solved? Like math theorems have proofs, right? A math theorem, I can read the proof. It's relatively short, right? So if we had like something to solve this, then maybe we can find something that actually does math and derives math theorems, right? And can prove things for us, right? So, all these recognition problems, if you can recognize a cure to cancer, then it counts as NP, right? If that was a search problem, like you stumble upon it and you can at least recognize it when you find it, okay, then that counts as NP. Okay, so, all right, so that's the theory of NP completeness. Any questions? Any fans of The Lion King? I don't believe you. Only 3 of you? How can that be? I was once the Lion King for Halloween as a child. Anyway, all right, so, okay, so just a historical note. This really happened over the course of 2 papers. The argument that any polynomial time algorithm could be turned into a polynomial time circuit, that actually comes first by 2 people, Cook and Levin. Okay. What comes a year or 2 later is this paper by Richard Karp, who pointed out all of these common problems that everybody was stuck on. Subset sum, Hamiltonian path, SAT, like tons of people are working on this, right? For operations research or for this or for that, for program verification. All these reasons you want to solve this problem. Maybe Hamiltonian path might be a simplified version of a routing problem. I want to visit all these places as fast as possible. That's a very basic operations research kind of problem. And we're all stuck and we can't solve anything. So Richard Karp was the one who tied it together with the complexity theory aspect of it. Okay, so this is a pretty amazing paper, reducibility among combinatorial problems. And just look at the abstract, it's so bold, right? A large class of computational problems, right? Like properties of graphs, like we've discussed, directed graphs, subset sum integers, arrays of integers, Boolean formulas, stuff like that. Right? And we can inquire into their computational complexity, right? It's reasonable to consider such a problem satisfactory if it terminates within a number of steps bounded by a polynomial in the length of the input. This was at a time when it was still somewhat debated as to polynomial time, whether it's important or not. Okay. And okay, we show that a large number of classic unsolved problems are equivalent in the sense that either each of them possess a polynomial time algorithm, bounded algorithm, or none of them does. Right? So this is a great abstract. Like, I hope your thesis will be similar. Okay. Yeah, here's another amazing way to conclude your first paragraph, right? Roughly the same abstract. But look at that last sentence. In this paper, we give theorems which strongly suggest, but do not imply that these problems, as well as many others, will remain intractable perpetually. Right? But a very enlightening statement, right? Because a lot of people are working on this problem, right? So this is really giving a lot of insight into the nature of computing and problem solving and trying to find algorithms. This is a really important moment. Okay, and then for whatever reason, I copied the whole algorithm into here, paper into here. I just want to show one. Okay, here he's listing a bunch of problems that are solvable, like shortest path you can do by part-type matching. We'll talk about that later. Here he's talking about MP and Cook's theorem. We didn't know about Levin because Levin was in Russia, and Russia was on the other side of Russia. Well, I mean, this was the Cold War, right? So we didn't actually communicate that well. Yeah, there's a great, all right, complete problems. And then here's some of the problems we've seen. Some more we'll see in following weeks, but like satisfiability, directed Hamiltonian circuit, undirected Hamiltonian circuit. Coloring, we'll do that at the end of class. You know, some more of these will come up in the rest of the class. And he put together this glorious chart where, you know, because he gives all the reduction in his papers, and this is how he goes from one problem to another. We often just went from 3-SAT to another problem, but you can, of course, you know, bounce around problems as you find convenient. So a very famous diagram. Well, we know that Cook's theorem, the Cook-Levin theorem, right? We know that all of these go back to satisfiability for free, right? Because they're all search problems. So satisfiability automatically solves all of them. So to go back up to the root comes for free from the Cook-Levin theorem, just because they're search problems. And in his paper, he showed, oh, finding the largest click can be used to solve satisfiability and, you know, node cover. And well, we haven't talked about all of these problems. Here's 3-SAT, right? 3-SAT can be used to solve SAT. And then chromatic number is fancy name for coloring. We'll do that in a moment. Coloring can be used to solve 3-SAT. Exact cover and so on and so forth. It's also impressive that I don't know how they draw these things as typewriters, but they managed to do it. Okay. All right. Okay, so that's his paper. There's a bunch of stuff in here. Just kind of going through one problem at a time. He doesn't draw nice pictures like we get in this class. All right, so that is all that. All right, I want to make one high-level comment. At the top of every homework, I suggested that, everything roughly boils down to two approaches. One is to identify the right subproblems to kind of efficiently break things down. I can interpret that in two ways. One is divide and conquer, where you really split up the input, right? But you have to identify how to split it up and understand something about the problem. And the other is like dynamic programming, right? Once you get the recursive spec, and it clearly captures that it boils down to a polynomial number of subproblems, you're just done, right? The implementation is often kind of easy. Okay, maybe there's some little bugs and you have to be a little careful. But the hardest part is the recursive spec, because that gets you to top-down kind of clear view. The other way to solve many problems in this class are reductions, right? Some kind of change the input. Whether recently it's been showing problems are hard, or like, shortest path and stuff like that. And every time half the class tries to reinvent Dijkstra's algorithm, it just looks so painful, and I'm just assuming that it's almost all wrong. Maybe it's right, but clearly it takes a lot of effort to re-verify an algorithm from scratch. It's so much easier if you can figure out how to change the graph and just apply the algorithm that we've already proved in painstaking detail, right? Because we already have all these nice properties about Dijkstra as a black box. They're all proven. You don't have to deal with it. As long as you understand what it does, all you have to do is change the graph. if you change the algorithm, you have to reprove things. It's a lot of work. It's hard to get right. I died again, I think. I'll just shout for a little while this charges. Okay, so there's roughly 2 algorithms identified, at some level, some reductive level, not 100%, but most of the time. But in relation to this theory of NP completeness, what I find kind of interesting is that on one hand, this whole idea of changing the input reductions was very important to realize, oh, independent set can be used to solve 3-SAT, right? That's 1/2 of this. On the other hand, this idea of this layered graph, or this, taking the computer and just copying the RAM over and over again, is a lot like Bellman-Ford, right? Which is a dynamic programming algorithm, which you can kind of think of as just copying the graph, where you take 1 step, 2 steps, 3 steps, right? And all those like layering tricks we do, red, white, blue, and stuff like that, right? It's roughly a layering trick argument to turn, what's sort of a graph with cycles into a DAG so that it looks like a circuit, right? So you guys have actually kind of done this implicitly in your homework before, right? So somehow this glorious thing comes down to 2 kind of tricks that actually we've been using over and over and over again all throughout the class. Okay, let's try this again. Any questions? Okay, so, all right, so in the time that remains, I was going to do one more of these hard problems. This is a classic problem, a problem that a lot of people are interested in. It's called graph coloring. Okay, so you take as input an undirected graph, and the goal is to assign colors to the vertices, right? You color 1 vertex red, 1 vertex white, 1 vertex blue, the American graph. Okay, and you want to use the rule is that you can't have 2 reds next to each other, or 2 whites next to each other, or 2 blues next to each other. So each color needs to form an independent set. And the goal is to use the minimum number of colors to properly color the vertices of the graph. So the decision version is, oh, I give you like a fixed number like 10 and say, oh, can you color in 10 colors or yes? 10 colors or less. And that turns it into a yes-no question. Okay, so for this graph, what is the minimum number of colors you guys can come up with? Again, I don't really know the answer. Yeah. Yeah. Yeah, adjacent means neighbors. So this vertex has 4 neighbors. So it's adjacent to this vertex, it's adjacent to this vertex, it's adjacent to this vertex. Oh, it has 5 neighbors. Adjacent to this vertex, and it's adjacent to that vertex. But like, for example, these 2 vertices are not adjacent. They're not connected by an edge. So adjacent means connected by an edge. All right. Has anyone figured out how to color this? Okay, how many colors you got? I will point to vertex. You just tell me what color. Okay, I'll start here. 1. Okay, that's a blue. Okay, how about up here? Okay, I'll call that red. How about here? Okay. How about here? Okay. How about here on the left? Okay. How about here? Okay. How about here? We need 4. Okay. How about here? Okay. How about here? Okay. How about here? Okay. All right. So that would be a 4 coloring of the graph. We use 4 colors, and every edge, there's different colors at the endpoints. Was anyone able to get 3? Okay, so 3 is impossible because we have a clique, a fully connected subgraph with 4 nodes. So you can't put 3 colors on those four. Okay, good. All right, so that means we have the right answer. Great. Okay, so, all right, what we're going to show is that even for k equals 3 coloring is NP-hard, which is to say that an algorithm for 3 coloring implies an algorithm for 3 SAT. Okay, so that means I give you a graph and I just ask, can you color it in 3 colors? Okay. 2, what about 2 though? Maybe just as a warm up. What would you guys do if I gave you a graph and asked you if it could be colored in 2 colors? Sorry? It's a greedy problem? Yeah, so what is the question really asking? Yeah, oh yeah, but yeah, so it's or not matching. It's just asking if the graph is bipartite at all. So it's also like part 3 of some recent homework, right? So, okay. All right, so 2 coloring actually is quite easy. That's the point. 3 coloring, somehow you go from 2 to 3 and things become hard. Sort of like 2 SAT and 3 SAT. Something weird about 3. Okay, but 3 is pretty restrictive. Okay, so we're going to try to show that 3 coloring is tough. All right. Okay, so high level approach we're going to take is that instead of going from 3 SAT to 3 coloring directly, I'm going to insert a problem in the middle called subset 3 coloring. I'll define it in a moment. And so we'll show that A, 3 coloring solves subset 3 coloring, and B will show that subset 3 coloring solves 3 SAT. All right, so what's subset 3 coloring? So it's like 3 coloring. You want to ultimately color the vertices in one of 3 colors, except for each vertex, I give you a subset of vertex colors you're allowed to use. So maybe the red, white, and blue are the 3 colors, and this vertex is only allowed to be colored red or white, and it can't be colored blue. Okay, so it's a slightly more restricted version of coloring. Okay, so you just have a small list attached to each node as part of the input. Okay, so can you guys hear me? Okay. Okay, so we want to argue that that a polynomial time algorithm for 3 coloring gives you a polynomial time algorithm for subset 3 coloring. The opposite direction is kind of easy. So the harder direction is, can I use 3 coloring to solve subset 3 coloring? Subset 3 coloring is the harder version of the problem. It's more restrictive. Okay. All right, so somehow we need to take as input an instance of subset coloring. That means you have a graph and you have a list attached to every vertex. Here I'm saying that, oh, there's no list attached to any color is okay. And turn it into just a graph with no lists attached. Okay, so I have to figure out roughly how to encode these subsets. Okay, so I give you a graph I give you an instance like this, right? So I give you a graph and I give you the subset for each vertex. Again, if there's no list there, that means that any color is okay. But I need to turn it into just a graph that doesn't have those lists that I can feed into a 3 coloring black box. This one's kind of fun. Any ideas? Yeah. Okay, so if I had a vertex, so if somewhere out there I had a vertex that was colored red and blue and I don't know how to draw white, okay, green, right? If there were vertices out there that are already colored red, green, and blue, right? And let's say that red is 1, blue is 2, and green is 3, right? So the suggestion is like, okay, let's look at like 2, 3. I mean, that vertex that is allowed to be colored 2 or 3. So it's allowed to be colored blue or green, but it's not allowed to be colored red. So ideally, I would like to add an edge like that. right? So that vertex is already colored red, and so that vertex can't be colored red anymore, right? I've effectively encoded that conflict or that subset by adding an edge. So we can keep going. So the vertex under it that's allowed to be colored 1 or 2, it can't be colored green, it can't be colored 3. 1 and 3, this one cannot be colored 2. 1 or 2, it can't be colored green. 2 or 3, it can't be colored 1, right? So if I had 3 vertices out there that were already given colors, red, blue, and green, then I could add these edges to effectively encode these subset constraints, right? But what's the only problem? Where am I going to get these red, blue, and green vertices? Okay, so this is the right idea, but I have to figure out how to get one vertex that's definitely red, one vertex that's definitely blue, and one vertex that's definitely green. Because that might not be part of the input. Sure, if there was some vertex that only had one color in its set, then it has to be, but we can assume that doesn't happen. That would be too easy. Yeah. Yeah, all 3. So we're going to make 3 new vertices. Okay. And we'll connect them with edges. Okay. Now, initially, these don't have any color, right? So the red, blue, green is a little bit misleading in that picture. So initially, just 3 new vertices we introduced connected by edges. Okay. But that triangle guarantees that all 3 have different colors, right? So whatever the coloring is, it's going to give 3 different colors to them. And I can interpret, each vertex being assigned a color as one of the colors, right? Like I can always like permute 1, 2, 3, like I can relabel things. It's not a big deal. So I can just go ahead and arbitrarily say, oh, I'm going to treat the top left vertex as number 1, the top right vertex is number 2, and the bottom vertex is number 3, right? So I think, yeah. So this kind of idea of a color palette. So all I know is that Y1, Y2, and Y3, which are the 3 new vertices, have to have different colors. And I can just arbitrarily decide, okay, I'm going to treat Y1 as color 1, Y2 as color 2, Y3 as color 3, and then connect it like we just did. Once I make those connections, I can erase the lists from the input, and all that's left is an undirected graph with no lists, right? So if you get a proper coloring, then it's going to give some coloring of this graph, and whatever color is assigned to Y1, I think of as color 1 and so forth. Okay. All right, does construction make sense? Okay. Right, so if you can properly 3-color the top graph, then it's not too hard to argue. I won't, in the interest of time, write out all the sentences. But if you had a 3-coloring in that auxiliary graph, then you can argue that down in the original graph, those colors will satisfy the subset constraints. And vice versa, if you had a coloring of the subsets, that satisfy the subset constraints on the input graph, then you just assign the small triangle up above correctly, and then you have a regular coloring on the auxiliary graph, right? So just go through both directions. It wouldn't be too hard, I think, for this one. Okay, so that is the first step of our overall argument, where this cute little trick of a color palette reduces subset 3-coloring to 3-coloring. Okay, excellent. All right, so the next step, why do I have this twice? Okay. All right, so the next step is the remaining one. All right, so I already know that 3-coloring solves subset 3-coloring. Now I just need to show that subset 3-coloring solves SAT. Put those 2 together, and then coloring solves SAT. Okay. So we're going to take as input an instance of 3-SAT and try to produce an instance of subset coloring. Right, so the extra subset part will help us in our reduction, make life a little easier. Okay. All right, so give you guys a chance to guess again. You take as input a 3-SAT formula, and you want to output some instance of subset coloring. Any ideas? Let me give a hint. Okay, I don't know how helpful this is. So we're going to ultimately have three colors, right? And it's convenient, you know, the colors are going to have some mapping back to 3SAT. So it's convenient to just name the colors as they will be interpreted. So I'm going to name one color as true, and sort of coloring something will be kind of like assigning true. It'll make more sense when the construction comes out. Another color I'll think of as assigning false. And I have a third color that sort of means neither. Not sure if that's helpful. Any ideas? So, okay, so you take as input a 3SAT formula. So you're starting with a formula. So your construction should be like, oh, for each variable, I make this. For each clause, I make this. Yeah. Okay, so maybe for a variable like xj, you're saying I should make a node. Xi also has a node. I'll make it a triangle, xk. Okay, so this is like, okay, so if I have a clause, I should make a triangle. So I have one node for every variable. I guess for every literal, right? So that means that if you're going to make one for xi and use it like this, you're probably going to want to have another vertex for xi bar, for when xi bar appears in a formula and stuff like that. Okay, we can try to interpret this. Okay, so if I have some triangle between xi, xj, and xk, then one of them has to be assigned true, right? Because it's triangle, right? So they all have to have three different colors. So this is saying that one of them has to be assigned true, one of them has to be assigned false, and then one of them is sort of this ambiguous neither. Okay, so the good thing about this is it's saying that at least one of the three have to be assigned true, right? You know, the color, that's good. But the thing about clauses is that the clauses don't say that one of them have to be assigned false. I would say that's maybe one slight conceptual difference, if that makes sense. But it's a good idea. It's a natural idea. Any other fun guesses? Maybe not. Maybe you'd rather start your spring break sooner than later. So I'll just go through it. Okay, so it's going to roughly be 2 steps. Okay, so for each variable, I'm going to make 2 nodes, one for each clause, xj and xj bar, which I'm calling aj and aj bar. Okay, and I'm going to say, okay, these can only be assigned true or false. I can only assign xj to be true, or I can only assign xj to be false as colors, right? Because it's subset coloring, so I can make subsets. So the subset's going to be true or false. And likewise, aj bar can only be true or false, because xj bar can only be true or false. And I'm going to add an edge between them, because that says, oh, if I assign xj to be true, then xj bar has to be false, right? Because they have to be opposite, and vice versa. If I assign xj to be false, then xj bar has to be true. Okay, so that's the first thing we'll do. The next thing is the clauses. This is a little bit more clever. I'll explain it. So for every clause with 3 variables, we're going to make this funny graph. Okay, exactly like this with exactly those labels. Okay, sort of a weird thing. Okay, so the claim is that, okay, so at the root it's saying that the top has to be colored true. And I'm going to try to argue that you can only color the top to be true if one of these 3 are true. A1 or A2 bar or A3 in this case was colored true. Okay, so where does this crazy picture come from? So the idea is that this is really consisting of 2 OR gadgets. Let me explain. All right, so look at that very simple 5 vertex graph. So it's a triangle with 2 legs. Okay, and it has some subsets. At the top can be true or false. The 2 middle ones can be true, false, or neither. And the bottom ones say can only be true or false. The claim is that you can only color the top one to be true if, that's not right, A or B is equal to truth. Sorry. Okay. So the claim is that the only way to color the top vertex to be true is if at least one of the 2 children was colored true. So to prove this, you just look at what happens if you assign both of them to be false. Right? If you assign both of them to be false, then maybe this one can be assigned neither, but then this one has to be assigned true. And that means this one has to be false. Okay, so if they're both false, then the top has to be false. Right, and that's all this little gadget of a graph is doing. So now when you look at this more involved one for a clause, what it's really doing is breaking up the 2 ORs into kind of like one at a time. One is an OR of the first 2 variables, and the other OR is an OR of the third variable, and whatever the OR of the first 2 came out to. Okay, so that's all this gadget is doing. So those are the 2 things you're going to do. Given a formula, you're going to make these vertices for all the literals, and you're going to make one of these gadgets for every clause. Okay, it can only be satisfied if you're able to color at least one of the variables true for every. Okay, I'll skip the proof again, which is to say I ran out of time to write the proof earlier today, but that's the overall construction. Okay, all right, so that's how we show that 3 coloring is NP hard, and have a nice, wonderful spring break. All right, thanks guys.